Welcome to week 2 of this introductory course on synchrotrons and X-ray free electron lasers. This week we will explore the basic features and physical description of the interaction of X-rays with matter. We'll begin by relating cross-sections and attenuation lengths for a given process, and how one can calculate one from the other. The only 3 relevant physical processes concerning X-ray interactions with matter are then introduced, of which that of Compton scattering is only very briefly described, as we will not consider this further in the course. The remainder of this, the first video of the week, will be concerned with the description of elastic scattering of X-rays by quasi-free electrons and the introduction of the concept of the atomic form factor. In the second video, refinements of the atomic form factor are added to account for the fact that the electrons in the material are generally bound to the nucleus with well-defined binding energies. Now, just as visible light is bent or refracted as it passes from one medium to another, glass to air for example, X-rays are also similarly affected. Now, how the refractive index in the X-ray regime is related to the atomic form factor will be covered in detail. From this, quantitative predictions can be made about refraction and reflection of X-rays. Lastly, absorption effects resulting from excitation of electrons to unoccupied energy states and subsequent relaxation processes will be discussed. Just a brief note about the tone of this week. Although it contains some mathematics, none of this is complex and should be understandable even for a high school student. So please don't feel intimidated by the introduction this week of some more mathematical expressions. Let's now begin by discussing the concept of cross-sections and attenuation lengths. Consider a process P, as yet undefined, occurring when X-rays pass through a block of material of depth L containing a number density ρA of atoms responsible for this process. Each atom has a cross-sectional area sigma p associated with the process. Due to this process, the beam intensity will exponentially decay as photons are removed or scattered from the beam as it travels through the medium. The attenuation length, lambda p, is defined as being equal to the length of the beam which has travelled through the medium before the original intensity I0 has been reduced by a factor equal to the natural logarithm E, which is equal to 2.718-ish. The relationship between this and the cross-section is simply lambda p is equal to 1 upon sigma p ρA. In order to better understand this, let's consider the example of a 10 kiloelectron volt X-ray beam passing through cobalt metal. In other words, an X-ray beam containing 10 kiloelectron volt photons. From the density of cobalt, which is 8.9 grams per cubic centimeter, and its atomic mass, which is 58.933, the atomic number density can be directly calculated to be 9.09 times 10 to the 10 atoms per cubic micron. The graph on the left of the photoabsorption attenuation length shows this to be 6.2 microns at 10 kiloelectron volts. Using the equation from the previous slide, we obtain a photoabsorption cross-section sigma PA of 1.77 times 10 to the minus 12 square microns. As there are 100 million square angstroms per square micron, this equates to 1.774 times 10 to the minus 4 square angstroms. Now, an even more convenient unit to use is that of the barn, which has an area of 10 to the minus 28 square meters, or 10 to the minus 8 square angstroms. Cobalt therefore has a photoabsorption cross-section of 1.774 times 10 to the 4 barns. Incidentally, a barn is approximately equal to the capture cross-section of uranium nuclei in fission reactions. The term barn comes from the colloquialism as big as a barn door, as scientists performing wartime research into uranium fission considered this to be a particularly large target and therefore a prime candidate for the development of the fission bomb. Now, even more whimsically, there exist, though admittedly only very rarely used and certainly not mentioned again here in this course, but there exist related cross-sectional units called the outhouse, equal to 1 microbarn, and the shed, which is 1 yoctobarn. So which processes should we consider when discussing the interaction of X-rays with matter? Nuclear and pair production only begin to dominate at photon energies above the highest presently available synchrotron facilities, the top end of which is shown by the yellow block here. As a consequence, these can be entirely ignored. This leaves only Thomson and Compton scattering and photoabsorption. All these processes involve the electron and the electron only. The nuclear core can be entirely disregarded due to its relatively large mass. A single nucleon is some 1,800 times heavier than an electron. We begin with a brief description of Compton scattering. This is a quantum mechanical effect in which some of the energy and momentum of an incident photon is imparted to a free electron, which thereby receives a change in its momentum. The energy lost by the inelastically scattered photon results in a lengthening of the wavelength and depends on its scattered angle psi and initial photon energy h nu 0, given by the equation shown here. The cluster of constants h upon mc is equal to 0.0243 angstroms. The relative energy loss therefore only becomes significant above a few tens of kiloelectron volts and for large angles psi, as can be clearly seen in the graph to the right. This threshold energy is related to the rest mass energy of an electron, mc squared, which is equal to 511 kiloelectron volts for electrons. As such, we will no longer consider Compton scattering in this course, although it shouldn't be forgotten when performing high-energy photon synchrotron experiments. Now we have seen that it is the electron which is the only particle of interest regarding interaction with X-rays. Let us begin by considering how a free electron responds in the presence of an electromagnetic field. In other words, light. Now, for non-relativistic electron velocities, so velocities much less than the speed of light, we only need to consider the electric field component of the incoming radiation. The magnetic component we can ignore. The electron will respond to this, moving in the opposite direction to the electric field, because the force is equal to minus the elementary charge times the electric field amplitude, big E. This causes the electron to re-radiate coherently with the incident beam, with the same phase and frequency, for reasons we will discuss later in the course in the beginning of the section on synchrotron physics. The intensity of the re-radiated or scattered radiation depends on the polar angle of observation chi, according to cosine squared chi, shown here. Hence, an observer viewing along the electric field vector at chi equals 90 degrees will see no scattered intensity, as the electric field has zero transverse component in this direction. Conversely, in the plane perpendicular to the electric field direction, scattering is maximized. Again, the reason for this spatial distribution will be made clear when we begin to discuss synchrotron or machine physics. This response of the free electrons to light is the reason why, among other things, mirrors reflect, radio antennas transmit, and, importantly, synchrotrons produce light. As I just mentioned, the reason for this will become very clear soon. This elastic scattering by electrons, that is, with no loss in photon energy, no change in wavelength, is referred to as Thomson scattering. Although the photon energy remains invariant, the direction or momentum can change. Let's consider scattering of a photon by an angle 2 theta, as shown here. The vector difference between the incident and scattered photon wave vectors, each of which have a magnitude equal to k, which is equal to 2 pi upon lambda, is equal to q, which is referred to as the scattering vector. The magnitude of q is easy to calculate as follows. Half of q is simply equal to k sine theta. It's a simple trigonometric relationship. I think we can all see that. Now, as k equals 2 pi upon lambda, q is therefore equal to 4 pi upon lambda sine theta. How strongly incident radiation is scattered by a free electron is given by the Thomson scattering length. This is determined as equating the classical electrostatic energy of a charge E at a distance equal to r0, which is defined as the Thomson scattering length. And we equate this to the rest mass energy of the electron, mc squared. The Thomson length thus turns out to be equal to 2.82 times 10 to the minus 5 angstroms and can be thought of as the classical radius of an electron. The cross-section of a free electron is determined by integrating over all angles of the dipole radiation and turns out to be equal to about 2/3 of a barn. We now progress from the case of a free electron to scattering from electrons associated with an atom. We begin by making the rather dubious assumption that all the electrons associated with the atom can respond entirely unhindered by the fact that they are actually bound to the atom's nuclear core. We first consider the limit of the X-ray wavelength being much larger than the extent of the electron cloud surrounding the atom. In this case, all the scattering elements will scatter coherently, in other words, in phase, because any differences in positions in space of the different cloud elements will be very small compared to the wavelength which is being used. As there are Z electrons in the cloud, the scattering cross-section is simply Z squared times sigma t, which, as you can see, is independent of the wavelength. So, for example, the low energy limit of Thomson scattering in the forward direction, shown here for the element barium, is 56 squared, because barium has Z equals 56. 56 squared is 3,136, and we multiply this by the cross-section of an individual electron. And when we do this, we find that we get a value approximately equal to 2,000 barns, as shown here. As the photon energy increases and the wavelength shortens to distances comparable and then even less than the size of the atom, scattering from the different elements dV in the electron cloud begin to interfere partially destructively, resulting in a drop-off of the scattering cross-section and therefore the intensity, which follows approximately an inverse square relationship with respect to the photon energy. The gradual crossover from the lower energy limit of constant scattering cross-section to that of one dropping off is at X-ray wavelengths comparable to the size of the electron cloud. In other words, of the order of about 3 angstroms, and when this equates to an energy, photon energy, of around 4 kiloelectron volts, as we can see is the case here. The precise drop-off is given by the atomic form factor or atomic scattering factor, F. This describes the elastic scattering amplitude as a function of angle, wavelength, and atom type. More accurately, F is normally expressed as a function of Q, or sine theta upon lambda, as this is the appropriate independent variable. If one performs one experiment at a certain energy and one observes the scattering at a certain angle 2 theta, then if we, for example, increase the energy, in other words, decrease lambda, then the same interference, in other words, the same phase difference between any two scattering elements dV of the electron cloud will be the same at shallower angles. So, for the example shown here for phosphorus, an atomic form factor of 10 electrons will be observed at high angles for low energies and low angles for high energies. Note also that in the forward scattering direction, all the electrons will scatter in phase, and the amplitude will be that of the individual electron multiplied by z. In other words, the total charge surrounding the atom. Now, the intensity, which is proportional to the square of the amplitude, thus increases with the square of z. The dependence of F on Q, or sine theta upon lambda, can be conveniently expressed as the sum of 4 Gaussians plus a constant, and values for every element for these expressions can be found in the international tables for crystallography. The expression is shown here clearly in this slide. Summarizing our discussion of elastic scattering so far, we should take home the following messages. The electrons respond to the electric field component of the incident X-rays and re-radiate as a consequence at the same frequency. The process is elastic, in other words. Now, at large wavelengths compared to the size of the atoms, scattering is independent of the photon energy, as the cloud can be approximated as being a point source. However, as the wavelength becomes smaller and then photon energy increases, scattering from the different volume elements within the electron cloud begin to be out of phase with each other, and this results in increasing destructive interference. As an approximation, the cross-section drops off as 1 upon E squared, where E is the photon energy, and is described in detail by the atomic form factor F, which is normally expressed as a function of Q, or sine theta upon lambda. In the next video, we will consider how the situation changes if we account for the fact that the electrons are actually not entirely free to respond to the incident radiation, but in fact actually bound to the atoms. This will lead to the phenomena of refraction, reflection, and absorption.